Hello. Today we're going to go over 15.2 general regions of integration, and this is with respect to double integrals. And so this will be similar to what we covered in the previous section, except that we're not going to be dealing with rectangles. So when we had rectangles, we were able to have constant bounds, like a number to a number and a number to a number for dx and for dy. When the region is not a rectangle, then we're going to have functions involved in our bounds. So it'll be important for us to examine like which order of integration makes the most sense. So I've got a picture here where our region of integration now is this blob D inside of a rectangle, okay? And so now that's this picture over here on the left. If we were to look at this in 3D, that same blob D, so that's like the set of the x and y values that we want to integrate over. And then the graph of f is our function z equals f of xy. So that's our surface. So we can see that we only want the part of the surface that is over that blob D. So we're going to deal with a couple of types of regions, two in particular. The first one is the type 1 region. And in a type 1 region, we will see regions where we have a y equals function up to a y equals function. And x will go from a constant to a constant. So one of them has to go from a function to a function. The other one has to go from a constant to a constant. So we have some pictures here where some are more clear. Like this first one is showing that x is going from A to B, while y is going from this g1 of x up to this g2 of x. And then in the next one, we have something similar, although it's not quite as obvious, right? So we have a sideways parabola in the second one, and we have to look at the vertex of that parabola as being the first x value, and then the cutoff is this x equals b. And then to break this up, since this is a parabola, g1 of x, it looks like would be the bottom. Or I guess it's bottom. I'm used to saying left and right of a parabola, but this is sideways. So g1 of x would be bottom of the parabola, whereas g2 of x would equal the top of the parabola. So we may have, the same function there, but it's like going to be a plus and a minus, all right? This next one, in order to make it a type 1 region where y is going from a function to a function while x goes from a number to a number, I can clearly see x is going from A to B. What is not so clear to me is the top function for y, because I've got this this V shape going on here. And so my inclination, if I saw this region and I was trying to set it up, my inclination would be to look at that point where there's a roof edge there, and I would draw a vertical line and figure out what what x value that corresponded to. I'm going to call it C for now. So in this particular case, it's like there's a G2A of x, and then there's a G2B of x. So they're like two roofs on this. And so in order to set this one up, I would have to look at two pieces. And in the first piece, I would have y is between g1 of x and g2a of x, while x is going from A to C. So that'd be the first part. The second part would be y is going from g1 of x again, but it's going up to g2b of x. And x is now going to start at C and go up to B. And so this would require a sum of integrals. And we'll see some problems like this, and sometimes it will make more sense for us to go ahead and use a setup where there are two separate integrals and we add them, but sometimes we'll make our lives harder by doing that. Sometimes we'll make our lives easier by doing that. So we'll just have to, play around and see what we come up with. All right, so that's kind of the picture side of it. The integral side of it is that our integral over the region D will now have the inner integral is the one that gets the functions for bounds. That is always, always, always true. If you set it up the other way, it's wrong. There's no other way I can say that. It is just wrong. You have to integrate the inner integral over the regions that are the functions. The outer integral has the constants. So if it's a type 1 region, then dx is where we have x values going from a number to a number, and dy is where we have y going from a function to a function. Okay? Let's look at an example of working through a problem that has a type 1 region. So in this particular one, I'm asked to evaluate a double integral over a region D of x plus 2y dA, where D is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. So I have a nice picture here already drawn. That's not always going to happen. In fact, it'll rarely happen. Usually we will need to draw our own regions and come up with our bounds. But looking at this, I can see that there is definitely a lower function for y, and then there is an upper function for y. I can't really draw a nice curve here, but there we go, that's better. And then I can also very clearly see I have an x values. I've got x starting at -1 and x going up to +1. So I can write this out. I can write out my type 1 region, and it's showing that the lower bound of y is 2x squared and the upper bound is 1 plus x squared, while x is going between -1 and 1. So that's how I'm going to set up my integrals. So this double integral over d of x plus 2y dA is equal to, now the outer bound, the outer integral must be the x values since those are constants. The inner integral must be the functions. So 2x squared to 1 plus x squared, and then my integrand is still x plus 2y, and the order is going to be dy dx. And of course, I can put in these little brackets in order to focus my eyes on the inner integral. So I need to integrate with respect to y. That is going to give me the integral from -1 to 1 of, looks like the antiderivative of x with respect to y is xy, and then of 2y squared will give me, of 2y will give me y squared. I'm evaluating this from 2x squared to 1 plus x squared. And then after I evaluate all that, then I'll deal with my dx. Okay, next line. I'm going to go ahead and evaluate. Everywhere there's a y, I will put in my bounds. So in the first piece, I have x times 1 plus x squared plus 1 plus x squared all squared minus, and now I'll plug in 2x squared for y. I get x times 2x squared, and then plus 2x squared all squared, and then this is all dx. All right, I need to expand, distribute, and then combine all my like terms. It's quite a bit of algebra that occurs when we're working with these. And I guess I should say it will pay off for you to actually do the algebra. Expand, distribute, combine like terms. It will save you time in the end. So if I distribute this first one, I get x cubed plus x. When I square the binomial, I get x to the 4th plus 2x squared plus 1. I'm going to distribute the negative sign at the same time that I do the multiplication in the next set of parentheses. I get minus 2x cubed minus 4x to the 4th. All of this dx. Now I'm going to combine like terms. So going in descending order, integral from -1 to 1, I have -3x to the 4ths I have negative 1x cubes. I have 2x squareds. I have 1x, and I have 1 constant. Okay, so simplifies things just a little bit. All right, let's go ahead and integrate. The first term is going to give me a negative 3 over 5, x to the 5th, minus 1 over 4, x to the 4th, plus 2 over 3, x cubed, plus 1 over 2, x squared, plus x. And this is going from minus 1 to 1. And then I'm going to go ahead and substitute this in, and I'm going to put it in my calculator after that. So if I substitute a 1, just remember all powers of 1 are 1. And so this gives me negative 3 over 5 minus 1 over 4 plus 2 over 3 plus 1/2 plus 1. All right, so that's evaluating at 1 minus the evaluation at negative 1. Remember, odd powers of a negative are still negative, and we're going to see a couple of double negatives in there. And then even powers of a negative will be positive. Since it's a 1, we're just looking at what signs we should get. So if I plug in a negative 1 to a 5th power, I'll get a negative, and then there's another negative outside, so that'll give me just 3/5. The minus 1/4, x to the 4th, I'm not going to be changing my sign because the 4th power, so this is just minus 1/4. The x cubed, the negative will be a negative, so I get minus 2/3. X squared, the negative goes away, plus 1/2. And the x, the negative stays. Okay, now I can go ahead and combine, the like fractions. So I do have a negative 3/5 and a negative 3/5 for a negative 6/5. I have a negative 1/4 plus a 1/4, so those go away. A 2/3 plus 2/3 will give me 4/3. 1/2 minus 1/2, those are gone. And a 1 minus a negative 1 gives me 2. So I can plug this into my calculator, and it gives me 32 over 15. Okay, so that's the process for type 1. Remember, the functions go on the inner integral. It's the most important part of the lesson. From there, there's a lot of algebra that's occurring and evaluating that's occurring. All right, type 2 region. So as might be expected, a type 2 is just like turning things by 90 degrees. So what we'll see in a type 2 region is that we will have left and right bounds that are functions. So we'll have x equals some h1 of y and x equals some h2 of y, while y is going to go from a constant to a constant. So we can see this clearly in this first picture. Y is a constant up to a constant, while x is going from a curvy function to another curvy function. In the second one, I see y going from a constant to a constant, and again, x is going from some curve to another curve. In the last one, this is another one of those where it looks like there are two lefts. I'm seeing right here, this little region right here. We could call that h1a of y, or we'll actually call that 1b. The bottom one that's on the left will be h1a of y. So on the left, I see two h functions, and on the right, I see one. And so this is one of those ones where I need to kind of break up it with a horizontal line. I need to break up my region and figure out the y value where that happens. I will call it E for now. And so then y will end up going from C to E and then E to D, while x is going from one left function to the right function and then the second left function to the right function. So we'll end up with two integrals. The first one will have bounds where x is going from h1a of y up to h2 of y, while y is going from C up to E. The second integral will be x is going from h1b of y up to h2 of y, while y is going from e up to d. And so we would have to look at a sum of integrals in order to handle this situation. Okay, so let's look at an example of a type 2. And in this particular problem, we have two pictures to kind of show you how to go from a type 1 to get to a type 2. Okay, so in this problem, we're asked to find the volume of the solid that lies under the paraboloid z equals x squared plus y squared and above the region D in the xy plane, bounded by the line y equals 2x and y equals x squared. So on the left here, you can see that they've drawn y equals 2x and y equals x squared, and they found where they intersect. That's occurring when x is equal to 2. And it's also occurring when x is equal to 0. So I can clearly see in a type 1, we would have x squared being the lower bound for y, and 2x would be the upper bound for y, while x would go from 0 up to 2. But I need to change this to a type 2 region. So they've done that for us. So in each of the equations, the y equals 2x and the y equals x squared, what they've done is they've solved for x. So in y equals 2x, we now have x is equal to 1/2 y. And instead of y equals x squared, I now have x is equal to the positive square root of y. If this had been the part of y equals x squared in the second quadrant, then I would have chosen x equals the negative square root of y. But this is in the first quadrant where x is positive. Now these intersection points are going to correspond with y values. So it looks like y is going from 0 up to 4. So if I write out my type 2 region, x is going from a function 1/2 y up to a function square root of y, while y is going from 0 up to 4. Okay, so we're asked to find the volume of a solid that lies under a paraboloid. That z equals x squared plus y squared, that is our integrand. That's the thing that gives us the height in our calculation of volume. So this gives us the height in our calculation of volume. And then the dx and the dy give us the area. So we'll have a height times an area, that's going to give us volume. So when I set up my volume integral, I have the double integral. Now remember, the constants go on the outer integral. So those are the y values, 0 to 4, while the x values will be, the lower bound is y over 2, the upper bound is square root of y. Our integrand is x squared plus y squared, and we're going in the order of dx, dy. Okay, so fortunately I have a little bit of room here. In order to integrate this, I'm doing so with respect to x first. And I actually want to rewrite my square root of y as y to the 1/2 power. It'll just make it a little bit easier for me to work with. So I integrate with respect to x. I still have the integral from 0 to 4. But now the integral with respect to x gives me 1/3 x cubed plus xy squared. We're evaluating from y over 2 to y to the 1/2. And then after we evaluate, we'll have a dy. So I'm going to go ahead and plug everything in. This gives me the integral from 0 to 4. I have, in the first evaluation, 1/3 times y to the 1/2 all cubed plus y to the 1/2 times y squared minus the second evaluation. That's going to give me 1/3, and then I have y over 2 all cubed plus y over 2 times y squared. And I'm a little bit off. I'm running out of room here. Hang on a second. almost feels like cheating every time I do that because you can't do that with paper. So I'll still have to deal with dy after I simplify this, but I need to simplify it. If you try to integrate this again with respect to y, you're not going to get it. Like, you need to combine things and clean it up. All right, so I'm going to clean it up. I have the integral from 0 to 4. I have 1/3. Y to the 1/2 all cubed is y to the 3/2. Y to the 1/2 times y squared is going to give me y to the 5/2 minus, and then I have a y over 2 cubed. That's going to be y cubed over 8 times the 1/3 gives me minus 1 over 24 y cubed minus the y over 2 times the y squared gives me a 1/2 y cubed dy. Okay, I can combine my y cubes. If I was to rewrite this as, so the minus 1/2 can be written as minus 12 over 24. So I can see how I combine those. I'll just do that one more combination. 0 to 4, 1/3 y to the 3/2 plus y to the 5/2 minus, it looks like I'll have 13 over 24 y cubed dy. All right, time to integrate. All right, the antiderivative of y to the 3/2 is going to be y to the 5/2 divided by 5/2, which will flip and be a 2/5. So this gives me 1/3 times 2/5 y to the 5/2 plus the y to the 5/2 when I integrate will give me y to the 7/2 divided by 7/2, which is just the same as multiplying by 2/7. Y to the 7/2 minus, and now here things are a little nicer, 13 over 24 times 1/4 y to the 4th, and we'll be evaluating these from 0 to 4. I lost my 2 in 24. There we go. All right, I just want to clean this up a little bit more and then I'll evaluate. Multiplying these fractions, I have 2 over 15 y to the 5/2 plus 2/7 y to the 7/2. 24 times 4 is 96, so I have minus 13 over 96 y to the 4th, all evaluated from 0 to 4. All right, now we're going to plug everything in. When I evaluate at 0, I'm not going to get any contribution because these are polynomial type functions and root type functions. So the only contribution is at the upper bound of y equals 4. So this equals 2 over 15 times 4 to the 5/2 plus 2 over 7 times 4 to the 7/2 minus 13 over 96 times 4 to the 4th power, and then minus 0. Okay, 4 to the 5/2. You can plug this into your calculator, but I'm going to do this kind of in my head. The half part, that means a square root. So the square root of 4 is 2. 2 to the 5th power is 32. So this gives me 2 times 32 over 15. All right, same thing with the 4 to the 7/2. The 4 to the 7/2, if I take the square root, that'll deal with the half power. So it's 2, and 2 to the 7th, I'm going to get 2, 4, 8, 16, 32, 64, 128. So I get plus 2 times 128 over 7 minus 4 to the 4th power. That is going to give me 256. Is that right? Yeah, 4 to the 4th is 256. So minus 13 times 256 over 96. And I plug those into my calculator. My calculator gives me a nice number of 216 over 35. Okay, so that is the volume that is contained if we restrict our domain to this region that's being drawn, and then we calculate the area of that and multiply it by the height of the paraboloid z equals x squared plus y squared over that region. Okay, so there are a few things to go over here. When it comes to general regions, we cannot just switch the order of integration without thinking about it. We can't just like change the integrals around, because remember, the outer integral must have constants. It cannot have functions in it. So drawing the region of integration is extremely important so that we can figure out how do we rewrite our functions so that we can see what our new bounds will be. Some other things to pay attention to. Sometimes only one order will work because of the region. So sometimes if you try to integrate with a type 1 region, it won't work because the function itself is not actually integrable in that variable. Like you need to do the other variable first, and then you'll have something you can work with. Sometimes the integrand makes it impossible to integrate in a particular order, so you must choose the other order. That's kind of saying the same thing. Sometimes you have to split your region into two pieces. I already talked about that earlier. And it'll be because they're like two tops or two bottoms, or there's two lefts or two rights. And so you have to split things up. And that just means adding up two integrals. Normally, we could define a double integral to be a volume, but if the integrand is just 1, then the height is 1. And if you multiply anything by 1, you get the anything that you had before. So in other words, if you take area times 1, you still get back area, right? So if our integrand is 1, we can use a double integral to find the area of a region of integration. So I've just got a little picture here that shows that, where z equals 1 is the roof, so that would be the integrand. And then we've got our little region down below, the region D. So here we've got a double integral over D of 1 dA. That's just going to give us the area of D. So if D is a nice region, like, I don't know, triangular, you can use a 1/2 base times height formula to calculate the area of that region, or you can go ahead and go through the integration. If our function is bounded below and above by some z values, where the z values are constants, then the integral can also be bounded by the integrals of those constants. So right here, I've got a function f of x, y. You can kind of see it's the blue that's in between two beige z values, little m and big M. So we get this inequality that our function over the region that we're concerned with is always between some horizontal plane little m and some horizontal plane big M. That means we could just double integral all pieces of the inequality to come up with this new inequality. So maybe we can't integrate our f of x, y. Maybe it's just something that is absolutely awful and there's no way for us to integrate it. But we do know that the function's trapped between two horizontal planes. Well, then what we could do is we could find an inequality, right? We should be able to integrate a constant. That's not a problem. So if we do that on the left and the right, we're going to get a number, and then we'll know that the value of our integral that we cannot integrate at least falls between two numbers. All right, here's some examples. We're going to set up an iterated integral for both orders of integration. And then after we do that, we're going to decide which order is the easier order. I should say I'm going to decide. And then whichever one is the easier order, that's the one we're going to do. We don't want to mess around with the harder order. Okay, so our double integral over d is of 6x squared dA, and d is bounded by y equals x cubed, y equals 2x plus 4, and x equals 0. Now what we have to remember is that x equals 0 is the y-axis. Okay, and then we need to draw this. So I'm going to draw kind of a tall y-axis. So 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go up 8 for y. 2, 3, 4. I'll go out 4 for x. And I'm going to draw y equals x cubed first. I know it goes through 0, 0, it goes through 1, 1, it goes through 2, 8, and it does that also in the third quadrant, but I'm not really concerned with that quadrant because everything is in the first quadrant. So this is y equals x cubed. Then I'm going to draw y equals 2x plus 4. That has a y-intercept of 4, so I'll go up to 4 and put in a dot. Let's see, when x is 2, I get y equals 8, so it looks like that gives us our intersection point, and I can draw this now. Y equals 2x plus 4. And it continues on to the left and the right forever. The last part that I have is x equals 0, which is the y-axis. And what that does is it gives us that closure that we needed, so we have a region D. So that's our region of integration. Now what we need to figure out, well, actually we were told to set up both orders of integration. So let's just look at what a type 1 would look like and what a type 2 would look like. Type 1. A type 1 region is where y goes from a function to a function. So it looks like the 2x plus 4 is in the bottom and the x cubed is on top. So we would see y between 2x plus 4 and x cubed. At the same time, x is going from 0 over to 2. Okay. With a type 2 region, I am seeing that my function, let's see, I needed another color, an extra color. My functions on the left, there are 2 of them. I've got the line from 2x plus 4, and I've got the axes. So I need to split these up. Fortunately, I can very conveniently see that this is y equals 4, where I'm splitting up. Okay, now I have a D1 and a D2. So I have 2 regions there. So I'm going to look at the first one, D1. D1, it looks like on the left, x is starting at 0. And then it is going to the y equals x cubed, but that is also known as x equals y to the 1/3. So I'm going to have y to the 1/3 for my rightmost function. And at the same time, y is going from 0 up to 4. So that's D1. D2, it looks like x is starting at the line 2x plus 4, which I need to solve for x in there. X would be equal to y minus 4 over 2. Okay, so x is starting at, I'll simplify that, 1/2 y minus 2, and it goes all the way over to y to the 1/3, while y is going from 4 up to 8. Okay, so it looks like to me, oh, we have to set up the iterated integral for both orders of integration. So let's do that. In the type 1 region, we would have the double integral over d of 6x squared dA is equal to the integral from 0 to 2, and then the integral from 2x plus 4 up to x cubed of 6x squared dy dx. So that's one way we could write it. But this is also equal to the type 2 region, right? It shouldn't give us a different answer. We should get the same answer regardless. But the type 2 region has us integrating over D1 and D2 and then adding those. So the D1 region, we go from 0 to 4. We go from 0 to y to the 1/3 of 6x squared dx dy plus the integral from 4 to 8, the integral from y over 2 minus 2 to y to the 1/3 of 6x squared dx dy. So I'm looking at these and I'm thinking it would be easier for me to integrate one integral than two integrals. My integrand is simple, it's just 6x squared. So that's not a complicated thing to integrate. Switching the order isn't going to make it any easier. In fact, it'll make it harder. So I'm going to make a declaration that type 1 is easier. And then I'm going to solve that. So I have 0 to 2, 2x plus 4 up to x cubed of 6x squared dy dx. All right, we are focusing on y first. We're going to integrate with respect to y. So we still have the integral from 0 to 2, and the antiderivative of 6x squared with respect to y gives us 6x squared y. We're going from 2x plus 4 to x cubed dx. All right, evaluating this, we get the integral from 0 to 2 of 6x squared, and in parentheses, I'll have my x cubed minus my 2x plus 4. So those are my two evaluations of y. 6x squared is just a constant. That's why I pulled it out in front. And then I'll still need to do dx once I simplify this. All right, distributing. This gives me the integral from 0 to 2 of 6x to the 5th minus 12x cubed minus 24x squared dx. All right, and when I integrate this, I'm going to get, wait a second, hold on. Let me see. You know what? I just realized something as I was setting this up. I wish I had somebody who could have stopped me before I made this realization. So my type 1 region is backwards. Oops. I need to flip those. I accidentally put the line on the bottom and the x cubed on top, and it should have been vice versa. The x cubed is the bottom function. So it should be x cubed and then up to 2x plus 4. And then I need to rewrite that in my integral. So I have 2x plus 4. Nope, I'm trying to do it again. I have x cubed on the bottom and 2x plus 4 on top. All right, and do that again here. So x cubed on the bottom, 2x plus 4 on top. Same in here. X cubed, 2x plus 4. You know, I could have edited this out, but I think it's actually better to show you that I'm human and I'll make mistakes too, because you're going to make mistakes. So now when I evaluate y, that y value, I'm going to evaluate it. I'm going to get 2x plus 4 minus x cubed. Okay, now I'll erase the last piece. So it wasn't hard to fix it. I just had to go through and find every part where I needed to fix it. Right, so this now gives us an integrand of 12x cubed plus 24x squared minus 6x to the 5th dx. Okay, phew, glad I caught that. All right, the antiderivative of this, we've got 12 times 1/4 x to the 4th, and so 12 over 4 is 3 x to the 4th, plus we'll get 24 over 3x cubed, which will be 8x cubed. And then we'll get a minus 6 over 6, x to the 6th. So just minus x to the 6th from 0 to 2. This gives me 3 times 2 to the 4th plus 8 times 2 cubed minus 2 to the 6th power, and then minus 0. There's no contribution from 0. And this works out to be 2, 4, 8, 16 times 3 is 48. 8 times 8 is going to give us 64. And 2 to the 6th is 64. So I have a final answer of 48. All right. So if I was to work this out using the type 2 region, I would also get 48, but I'm not going to work it out using the type 2 region. the directions say to pick one, so I picked my 1. All right, next example. We want to evaluate a double integral, and it's the double integral over d of y squared dA. And our D, our region of integration, is a triangular region, and it is bounded by points 0, 1, 1, 2, and 4, 1. I'm realizing the time on this, and I think, yeah, I'll do this one problem and then I'll do a part 2 video. Okay, so very first thing, draw the region. So I'm going to draw an XY axis. It looks like I just need my first quadrant. And I need to put these points on here. I have the point 0, 1. I have 1, 2, and 4, 1. Connect the dots. And this is going to be my region of integration. That's my D. I'm going to give these vertices names A, B, and C because I actually need to come up with the equations of these lines. So that's kind of the hard part. But it's helpful to see them so I know that I have to do that. So I have the line AB first. AB, it looks like, has a slope of 1 and a y-intercept of 1. So y is equal to x plus 1. That one wasn't bad. Or it could be x is equal to y minus 1, depending on how we set this up, okay? The line BC, that's a little bit more work. My slope I can figure out. My slope, I go, it's down 1, so I have a negative 1, and then it's over 3. So I have a negative 1/3 for my slope. But then I need to use the point slope form of the line to come up with my y-intercept. I don't know what that is. So I'll use the point, let's see, I can use 1, 2, or 4, 1. I'll use 1, 2. Y minus 2 is equal to negative 1/3 times x minus 1. So y is equal to negative 1/3 x plus 1/3 plus 6/3. That's the moving the 2 over. So this simplifies to be y equals negative 1/3 x plus 7/3. Or if I multiply by 3, 3y equals negative x plus 7, or x is equal to 7 minus 3y. Okay, last line is the line AC. That's a horizontal line. It's just y equals 1. There's no other way to write that. It's just y equals 1. All right, so what we need to do is figure out which type we should use, type 1 or type 2. Now I'm going to move that little d out of the way, put it over here. Okay, I'm noticing that this particular function or region that I have here could be split vertically at x equals 1. And the problem with that is then it like the reason that's happening is it's like there are two tops, right? This is top 1 and this is top 2. I don't want to deal with that. I would rather deal with one left and one right than have two tops, because that's going to mean I have two integrals. So if I do type 1, I have two regions, which means two integrals. So I'm not going to do that. Instead, I'm going to do type 2. It just has one region. And that region, the left function is AB, right? So x is going to go from the line AB to the right side, which will be the line BC. So I can write that better since we have our equations. That means x is going from x is going from y minus 1 over to 7 minus 3y, where I just wrote down those lines that I found already. And then at the same time, y is going from 1 up to 2. So that's not too bad. Let's go ahead and use that. This means that our integral will be the double integral over d of the region, or the integrand was y squared dA. We can rewrite it as the integral from 1 to 2, the integral from y minus 1 to 7 minus 3y of y squared dx dy. I'm integrating with respect to x first, which means I'll get y squared x. So this is the integral from 1 to 2 of y squared x, evaluated from y minus 1 up to 7 minus 3y dy. And then that y squared is like a constant, so this is the integral from 1 to 2 of y squared times evaluating x at 7 minus 3y minus the evaluation of x at y minus 1. Make sure you have parentheses there, and then dy. So I need to distribute and get like terms and then distribute it again. This will give me the integral from 1 to 2 of y squared times, it looks like I have minus 4y's, and I have 7 plus 1 for 8 constants. Now distribute one last time, the integral from 1 to 2 of minus 4y cubed plus 8y squared dy. Okay, now I can integrate with respect to y. The first one gives me negative 4 over 4, which simplifies to a negative 1, y to the 4th. And then the second one, 8y squared, becomes plus 8 over 3y cubed. This all gets evaluated from 1 to 2. So I'll write that out. We have negative 2 to the 4th plus 8 thirds, 2 cubed. That's my first evaluation, minus my second one. I get minus 1 to the 4th plus 8 thirds, 1 cubed. So the first one, 2 to the 4th is 2, 4, 8, 16. So negative 16 plus 2 cubed is 8. 8 times 8 is 64 over 3. Minus, it looks like those ones aren't going to make any change, so I'll go ahead and distribute. I have minus a negative 1 for plus 1, and then minus 8 thirds. So this is going to give me negative 15, and then plus 56 over 3, and I can pop that into my calculator, and it will give me, hang on, I'll go ahead and do that. So I have 56 divided by 3 minus 15, and that gives me 11 thirds. And that's my final answer. So this is, part of the process that you'll have to go through. The actual integration is like one step. It's super easy, or 2 steps. We have 2 integrations, right? But the setup is like half the page. And then the algebra is a big part of it too. So you have to be very careful with that. All right, I'm going to go ahead and end this right here. And when we come back, we'll do the last 2 examples.